Alright, so this tutorial is the first of 3 lessons on the kinetic theory of gases. We're going to start with macroscopic properties of gases. We're going to look at then gas laws, and then we're going to turn our attention into the microscopic foundation for that. This first tutorial will look at what it means to be a liquid solid gas from a macroscopic and a microscopic point of view, and then define 4 important properties of a gas that work at both levels. Then after that, we will develop the gas laws from a conceptual standpoint. I'll do another tutorial for that. And then lastly, either in class or through another tutorial, we will look at the quantification and the molecular theory behind it. Okay, so let's start with what it means to be a liquid, solid, or gas again. This is a review, but then we're going to see how this builds up into especially properties of gases. So what's the difference between a solid, liquid, and a gas? Well, from a macroscopic standpoint, it all really has to do with their shape and their volume. Solids have definite shapes and definite volume. You leave it alone, it's not going anywhere. It's not going to start flowing, and the volume stays the same unless you chop off a piece. Liquid has no definite shape to it. It is a fluid, okay, but it does have a definite volume. You spill a glass of water, and it was, let's say, a cup of water, you're still going to have a cup, even if it's spread out in a pool or a puddle. Gases, on the other hand, have no definite shape, and they have no definite volume. The latter part is not as obvious, but if you take a container full of gas, let's say perfume, and you spill it through diffusion, it will eventually fill up the entire room. So it takes on whatever shape the container has. So from a microscopic standpoint, this is not hard to understand. We know that in solids, molecules are held together by bonds, right? And they vibrate in crystal lattices. Okay, structure to it. So they're jiggling back and forth, but they're not going anywhere. And so we say they have those bonds between them, even though it's a vacuum between one molecule and another. They are held in place, if you will, by those intermolecular bonds. Liquids, on the other hand, have more freedom to motion. So one way of looking is they vibrate, and this is not maybe the best way of putting it, but they vibrate in sheets. Okay, so they vibrate along, they're kind of held in place along a plane, but different planes will slide across one another, and there's where your fluidity develops. But it's not complete freedom of motion. So if you want complete freedom of motion, you input more and more energy, you break apart the bonds, you make them weaker, and then when you get in the phase change of a gas, you have essentially no intermolecular forces. And you have complete freedom of motion. And because of that complete freedom of motion, you don't have a definite shape. So where the gas is all depends on what container, if you will, you're talking about. Okay? So with that in mind, we want to look at different macroscopic properties of a gas that just make sense to measure. If I have a gas, what is the easiest thing to measure about them? And turns out there's 4 key measurements. So we're going to look at them from both the small and the large. So let's start with ones. We're familiar with all these. So one is temperature. So it makes sense to talk about the temperature of a gas. A very, very important property. So what is the temperature of a gas? Well, it's proportional to the average kinetic energy of the molecules, not the internal energy. Internal energy is the sum, right? It's really the sum of the kinetic energy of all the molecules. That's very, very different than the average of any one molecule. And it's key that you make that distinction. So temperature is not kinetic energy. They have very different units, but there is an intimate relationship between them, which we'll develop later on. Okay, so since it's based on the motion of those molecules, there's actually 3 ways that they can move about. You can quantify that kinetic energy. The most obvious is translational. That's just going back and forth in X, Y, and Z direction. Okay, so we'll focus on that. But you gotta also recognize, if you do a complete understanding, there's rotational. If you think of what's the word I want? A molecule made up of 2 parts. A diatomic molecule, sorry. This can be tumbling about, rotating about this axis. It could be rotating about the axis coming out of the board, etc. And then if you imagine also those bonds as like a spring, you can get vibrational motion. Okay, but by and large, our analysis is going to focus on just the translational, because that's the easiest way to approach it, and then you can always make it more complex later on. All right, second macroscopic property that makes sense is volume. Okay, even though a given amount of gas has no definite volume, we know that it will fill its container because the molecules have the freedom to move around, and as they collide with each other, they will fill up the entire vessel that holds it. As such, and I'm going to skip 3 for a second, if it's enclosed in a vessel, then those molecules are going to hit the walls of the vessel. And if they hit the walls of the vessel, they are going to collide with it. They're going to exchange momentum, and they're going to exert, of course, a pressure. Okay, so you got collisions, and the collisions are between the molecules and the walls. We're not talking intermolecular collisions, one particle hitting another. So if I've got a container and I've got molecules bouncing about, okay, they will exert a pressure here, but if I have 2 molecules that bump into each other here, we don't really care about that. It's not registered. There will be an exchange of kinetic energy and change the average kinetic energy of each, they'll change the energy of each other, but they won't change the overall kinetic energy. That's an important distinction to make. All right, so the last quantity we want to talk about is simply the amount. Okay? The amount of gas can be measured 2 ways. There's the obvious way, which is mass. But the other way that we're going to focus on here is the amount in terms of literally amount, and that's measured in moles. And moles is a fundamental unit of physics, okay? Just like masses. So moles is kind of like a count of it. The symbol for mole is lowercase n, and there's 2 ways of looking at it. It can be defined as little m divided by big M, and it can also be defined as big N divided by n sub a. All right, so these are all terms, believe it or not, you've learned before, and so I'm going to review what they are. All right, little m is mass, so I'm not going to write that down. Big M is molecular mass, or I want to say molar mass. I think they're the same thing. Okay, so molecular mass is like grams per mole. Very often we might have to do kilograms per mole. All right, so if I have, let's say, helium is really H, we'll assume it's H4, so that would be M is 4 grams per mole. All right, we'll see what that comes in later. So it's basically the amount of moles is if I have 8 grams of helium, all right, the amount of moles I have is 8 grams divided by 4 grams per mole, which is obviously 2 moles. Okay, so that's pretty straightforward. Another way to look at it is the number of particles. So N is the number of molecules or atoms in question, and Na is a special amount. That's Avogadro's constant. Okay, and Avogadro's constant, Avogadro's number, is fairly familiar to us, but if you've forgotten, and I might have this part, I think it's 6.02, I'm not sure about the 2 part, times 10 to the 23 particles. Okay, so if you have 1 mole of gas, doesn't matter what the gas is, you have exactly that number. All right, so if I go, how many atoms are in 8 grams of helium? Well, I've already done 1/2 of it. I figured out that I have 2 moles, and so now I can say N equals N over Na, therefore N equals 2 moles times 6.02 times 10 to the 23, and you get the idea of what that answer is. All right, I'll let you fill that in. So that's a trivial type of problem, but it's something you have to be able to do to lead to more complex problems along the way. So don't just gloss over this. Make sure you understand each part. If you don't, certainly come in with questions. All right, so that wraps up our first part. What are the macroscopic definitions or properties of a gas, and where does a gas fit in with liquids and solids in terms of molecular structure?